Hi everyone. Today I want to talk about integrals of the form where we have a quotient like this. So if I had the integral, let's see if I can get my pen working. If I had the integral of f dash x over f of x with respect to x. Now this is a good example where we might use substitution method, which I discussed in the previous video, because clearly the derivative of f of x appears somewhere in this expression. So I will go to the side here and say let u equal my function f of x. Then the usual process is to take the derivative du dx, and by definition that is f dash x. Now we at this point want to isolate dx, so I have f dash x as a denominator and that equals dx. I'm now ready to do my substitution over here. So f dash x still appears in the numerator. F of x will be rewritten as the substituted x variable u, and dx will be rewritten as du over f dash x. Now, as we're accustomed to with this method, the f dash x component cancels, leaving us a very simple integral of 1 over u du. And that is ln, the natural log, of u plus c. Now, I will then just replace u with the original expression f of x plus c. Those are absolute value signs. They're just a little bit too wide for my liking, those absolute value signs. Let's just put them a bit closer to make it a bit neater. There we go. That's a pretty important result. Now, you may have in the past seen the integral of 1 over x. You might have seen that integral of 1 over x dx equaled the natural log of x. That's just a particular case of this more general rule that I've done here. Obviously the derivative of x equals 1, so the form of this rule follows along this, but this is much more general now. We could use this it'll be more applicable. So let's try a couple of examples, not too many. The one that springs to mind would be something like the integral of tan x. So I'll write this as sine of x over the cosine of x. Now that's not quite. It's almost a derivative. Derivative of cosine x is the negative sine of x. So if I really wanted this to be in the form, I'd need that to be negative sine of x. That's exactly the form of my rule, but I can't just throw a negative sign in there for no reason. So I'll put a negative sign, like negative 1 at the front here, multiplied by, to keep everything true. So now I'm in business. I've got the negative 1 at the front, and what is the integral? Well, it's the, if I go back to my rule, where was I? So I've got something which is exactly of this form, and the integral turns out to be this. So it's the natural log of the function in the denominator. So it's the natural logarithm of the cosine of x plus c. That's my integral of tan x. Now I could make this a little bit neater. The negative sign at the front is a little bit of a nuisance. So what if I wrote the cosine of x to the power minus 1? And I hope we all remember that the reciprocal of cosine is secant. So that's how we would use this rule to find something like the integral of tan. Now it doesn't just work with trig ratios. We could also do something if we had, say, the integral of, let's do something a bit more general. What if we had 1 divided by ax plus b. Now the derivative of ax plus b is a. I would really like to have this expression as a over ax plus b. Then my rule would apply because the derivative of the denominator is the numerator. Now I can't just multiply everything by a for no apparent reason, so I'll have to write the constant 1 over a at the front of this integral to make sure that everything remains true. Now I can apply my rule. The 1 over a is still there, and the rule for this is the natural log of the function in the denominator, ax plus b plus c. There you go. That's a nice little quick explanation, I suppose, of how we use integration by substitution to find this lovely new rule here when we happen to have the situation that we're integrating a quotient and the numerator is the derivative of the denominator. We can go straight to this rule. Saves us a lot of time. We don't have to do the full substitution process every time because that rule applies no matter what the functions are. That's all for now. See you next time.